Good morning all. I'm Takia Williams and I'm a Standards Development Manager in charge of the UK's National Robotics Committee. Welcome to our Exploring Robotics Innovation webinar. We've put this webinar together to give you a first-hand perspective from national experts shaping the UK's robotics standards and to help you understand how your organisations can align with this work. Next slide, please. So this is just a bit of housekeeping for you all. So this is a listen only webinar. So you'll notice that your microphones and cameras have been disabled for the duration. If you have any questions, please do submit questions via the submit questions button and they'll be addressed at the Q&A section of this presentation. If you have a specific question for a specific person, please note that in your question. If you do have any technical issues, please report them through the same question button. After completing the event, there'll be a feedback survey and BSI will provide that link for you with the recording, after the recording. This is a CPD accredited webinar, so to request your certificate, you can do that after you've completed the survey. BSI hosts various webinars throughout the year or events, and to learn more, please do scan the QR code below. Thank you. So I would like to introduce you to our first speaker today. This is Jane Byford. So Jane has over 20 years experience in the aerospace manufacturing industry. Jane specializes in machine safety, COMAH, and the safe development and deployment of emerging manufacturing technologies. She's been an active member of BSI's Robotics Committee for several years and has worked closely with Make UK and the Health and Safety Executive on the development of safety standards for industrial robots. Jane brings deep practical insights into integration of advanced technologies within high-risk environments with a strong focus on influencing human factors and integration of new technologies in the working environment. Over to you, Jane.
Good morning, everyone. Thank you for attending. So I'm here to talk to you a little bit today about safety compliance for future manufacturing. Next slide, please. So flexible manufacturing is a must for businesses to become and remain competitive in the modern environment. The days of where you set up a system and that stays in place for a number of years while you build a known component is now moving on, and the requirement for facilities to be more agile and reconfigurable is paramount in a lot of businesses, and especially in the aerospace industry at the moment. So we have a technology research department, and quite often they come to me and say, we want to set up a sandpit environment. And that sort of fills me a little bit with the sort of feelings of doom, because you know that this is going to be a challenge to try and make sure that it remains safe and remains compliant, because everything is changing as they try and reconfigure these systems and test them out. So the aim would be, in a lot of cases, that a facility is designed so it can be reconfigured within a shift rather than within several months. So, the speed required is quite challenging. Maintaining those standards and compliance to legislation is a real challenge. Change management is absolutely critical in this, because moving away from the design standard very rapidly then means that you can lose configuration control quite quickly. Next slide, please. So trying to achieve compliance is complex. You are basically dealing with a number of components that are existing, established elements that you can buy off the shelf, robots, not new, they've been around for a long time. However, trying to create a new cell where the technology readiness level, the TRL, is quite low, because you are adding different components into that system and constantly reconfiguring it is a challenge. The integration creates a new assembly of machinery. So the integrator becomes a real a real sort of important component of the overall manufacturing facility design, and understanding what the business needs from that design facility and what it might turn into. So the integrator ends up having to apply a CE mark to this, so saying that it complies to a number of different standards, and it, you know, they've done the design risk assessment, so that they sign it off. However, the employer that has commissioned this facility might then decide through its design team and reconfiguration that they are going to add a number of different factors to that. Now, the question is bringing back the integrator, or actually maintaining that as an in-house capability. So that then means that they are going to have to take on the responsibility for design risk assessment, keeping up with technical documentation, and then sort of making sure that that change management continues and that it complies. It is a very challenging problem, especially, next slide please, when you're modifying capability. So if you add new robots, new sensors, new safety systems, or you're getting new software and firmware updates, the cybersecurity elements in that obviously is going to be quite a big part of the new machining regulations that take over the machine directive in 2027. So there's a lot to be considered. Motion control systems require revalidation, and you must prove that the system meets all the safety performance levels as you go along. Robots, again, as I said, were not new. Collaborative robots were always thought to be sort of ones that you could work next to, and they were sort of relatively low torque. However, the capability of those in an actual manufacturing environment is relatively low. So we are looking at industrial robots being used in a collaborative way. So those safety parameters become really, really critical in design factors when you start reconfiguring these new cells or even setting them up. Next slide, please. And end effectors add an extra complexity to this. So for a robotic cell, you could start off with the robot just holding a fixture. However, that once it's in place, you may want to do some drilling, or you may use the robot to spray or carry out a quality task, or even do some drilling. So there's quite a lot of different aspects to consider when the robot cell is being put together. And again, the size of the end effector. If you're designing a cell, you may have an end effector that needs to deal with quite small components, but equally quite large components. And that then becomes a constraint of your safety system. You need to make sure that its movement is within the safety envelope of your design solution, rather than risking it moving outside of that and then becoming a hazard to any other activity going on around that. So you need to make sure that the way it's designed is make sure that that safety envelope is critical and has the right safety margins conforming to all the standards. The reliability of the safety functions when all of this change is absolutely crucial. Testing and making sure that all the parameters continue to work, again, is complex. It's not an easy thing to just change a set of parameters in the safety control system. They have to be tested, make sure they work right, and make sure that they are actually sort of containing the risk to the designed envelope. All of this, if you are constantly adding, could invalidate any CE mark that the original integrator put on that system. So that's where a challenge then becomes sort of paramount for the employee to remain sort of in that configuration control and moving on with its CE marking and making sure that it's adding all those risks to that design assessment, making sure it complies with the standards, and also then sort of is proving out to be safe. Operator hazard risk assessments, again, you know, once we've moved on from actually installing the facility, we've then got to try and make sure that we keep the operators clued up with the risk assessments, which is a different challenge, but it is a constant challenge, especially in today's digital world where people tend to read less and they need that information coming to them on quite a constant level to keep focused in on what's going on, especially if you're moving between shifts and those parameters have changed. Communicating those risks become a challenge. Next slide, please. So what do we have to actually sort of control that? We've got the provision and use of work equipment regulations, and sort of the supply of machinery safety regulations come into this. Obviously, if you are then responsible for creating this machinery, you need to make sure that it's complying with the essential health and safety requirements. And then as an operator, you then got to make sure that it's safe. However, these regulations are quite old. They're not really set up for the agile manufacturer, because when you start reading the hierarchy of controls, you know, in the world previous, it was put it in a box and guard it, and that was absolutely right for the time. However, these days, putting it in a box is not always the desired manufacturing solution that the employer wants. They want that agility, they want that flexibility. It needs to stay safe, so you are looking at more of the softer, sort of in the light guards, that type of thing. So there's no physical guard, and where you then potentially have ejection risks, that becomes a problem with some of the risks that you may need to then make sure that you are controlling and containing as well. So they are quite old regulations, and we found where we've been looking at our factory of the future development environment, that actually engagement with the HSE and bringing the HSE SME in and saying this is what we're doing, and not being secretive about it, and bringing them in and getting them involved has been an absolutely massive, powerful tool, because they've been able to come in, give their advice, look at what we're doing, understand where we're coming from, and they're also part of standard development as well. So they understand the risks that are now being faced by an employer in trying to deliver a safe solution for their workforce, but also try and comply to the regulations as well. Next slide, please. The standards that we're looking at, obviously, there's a little graph here that I've put in. I've also added some extra bits on this. So you might find this in Annex B of 10218, which is the safety requirements for industrial robot standard, which is a really excellent standard and one that we've been involved in. And from my perspective as an employee, as an actual sort of trying to use that standard, it's really good to give others an insight of how practically we try and use it. That standard is great. However, there are other things now bringing in from the new machining regulations around cybersecurity, and obviously that's predominant in the news at the moment because of certain cyber attacks. That is essential to make sure that these robotics facilities stay safe, and there's human factors as well, which Sarah will talk about a little bit later. But again, really important on how operators interact with these work cells. Next slide, please. Next slide, please. Thank you. So it can be very difficult to distinguish between major and minor changes to your workplace. New risk profile, you need new conformity assessments, and if you're just doing a minor one, is it within the original CE marking scope? You've got to be on it and just checking all the time. The machine regulations, Annex 3, which is the essential health and safety requirements, not sort of changing that much, but still need to be taken into account. Technical file, all of those need to be kept up to date, and it may be the integrator that continues to do this for you, or it may actually be the employer. Interface issues with other applications, so you may want to widen sort of like the robotic cell and sort of bring in other aspects to interact with it, and that then becomes a completely new piece that you then have to make sure that you've got included on your design risk assessment and then follow through with the CE marking. So there's all sorts of complexities around this. Next slide, final slide. So managing through change, embed good practice at design stage. Can't emphasize enough. Safety involvement on these cells is absolutely massive. When the design engineers get going with stuff, the sky's the limit. They really want to sort of bring it in everything into their cell and try and make it all work at once. So being a safety professional involved in that at the beginning, you can always then sort of like moderate and say, right, okay, well, we need to think about this. Safety should never be considered as a handbrake to things. It's an enabler. It's to say we can do this, but we need to make sure that we look at all the standards, because there's lots of elements in there that provide good practice to actually help us achieve our goals in establishing these new work cells. Change management, deviating from the original design is, can quickly happen. So that change management is absolutely essential to all the aspects that are involved in that. Establishing really good practice, even working this out in a digital twin, that can be really, really great. Digital twins, really help designers leaps and bounds and sort of planning work and the sort of working out how things might work. However, when you get the Mark 1 human being into there, it doesn't, sometimes you get different parameters that sort of give you different challenges. So, they have their absolute uses. And then looking to the future, we've got the change to the machine directive through the machine regulations for Europe. Now, UK are sort of still complying with European standards. Hopefully, in my opinion, that we should continue with the European, because it makes it so much easier, because a lot of the equipment is coming in from Europe in other ways, and it all complies, and it makes life a lot easier for us. Modular declarations will simplify multi-robot sort of configurations. And smart factories will continue to need this dynamic response. So this is something that we will need to get used to. So embracing this now is really essential. So thank you for listening. Any questions, please drop them in the chat box and Takia will moderate. Thank you.
Thank you so much, Jane. So now I'd like to welcome Alan Winfield. So Alan is a professor of robot ethics at the University of the West of England, visiting professor at the University of York, and associate fellow of the Cambridge Centre for the Future of Intelligence. Alan co-founded the Bristol Robotics Laboratory, where his research is focused on the science, engineering, and ethics of cognitive robotics. Alan is an advocate for robot ethics. He chairs the advisory board of the Responsible Technology Institute at the University of Oxford and has co-drafted new standards on ethical risk assessment and transparency. Over to you, Alan.
Thank you very much indeed, Takia, for that introduction. So I'm delighted to be part of this webinar. If I could have the next slide, please. So I'm going to introduce a British standard, BS 8611. Clearly, there isn't time to go into a great deal of detail, but I'm going to give some examples of how we've actually used BS 8611. So what is 8611? Well, it's actually a method for doing ethical risk assessment. And I believe it's an extraordinarily powerful and useful method. So next slide, please. So what is ethical risk assessment? Well, essentially it's risk assessment that has extended the envelope of risks from straightforward safety risks, for instance, to include psychological risks, that's risks to the individual, psychological risks, and societal risks. And of course, those societal risks might also be economic, as well as risks to democracy, for instance. That sounds a little bit mad, but I hope you get the idea that ethical risk assessment extends the envelope of traditional safety risk assessment. Next slide, please. So the first case study I'm going to show you is a fictional robot, and this is a paper that we published in 2020. We've taken a fictional robot toy called RoboTed, and we've then conducted an ethical risk assessment on that robot. I'm not going to show the entire ethical risk assessment, but I will give you a couple of examples. The paper is open access, so feel free to go and find it if you're interested. So next slide, please. So here is our psychological risks assessment. And you can see the table has 3 columns. The first column is the hazards column. Now, a hazard is defined in BS 8611 simply as a possible source of ethical harm. And a risk in the middle column is a possible ethical harm arising from exposure to that hazard. So, for instance, the very first example on the table is addiction. And the risk from that particular hazard, for instance, is that a child plays with Ted and obsessively and neglects their family. So the mitigation would, for instance, be that Robo-Ted has a built-in function, I need to sleep now. Of course, robots don't need to sleep, but nevertheless, that would mitigate the risk of a child becoming addicted to playing with this teddy bear. I'll go down to the third one, which you might be interested. This is the hazard of over-trusting by parents. And I haven't told you this, but in this case study, we imagine that the Robo-Ted has a childminder function. Now, in this risk assessment, we've decided that actually the risks of that function are very high, and therefore the mitigation is to remove that particular function altogether. And that just illustrates that ethical risk assessment at design time can actually both change but also remove functions from the specification. So next slide, please. And this, I think, is, I hope you'll find interesting. This is privacy and transparency risks. So, for instance, the first one is weak security, the hazard, and the risk is that hackers gain access to Robo-Ted's sensors and control functions. And the mitigation would be to implement strong encryption together with best practice password protection. And the final one I'll highlight is lack of transparency. And this is a lack of data logs, which makes it hard or impossible to investigate accidents. So the mitigation is to build a secure local data logger into Robo-Ted. Next slide, please. In fact, we had a paper in 2022 which applied the same technique of ethical risk assessment based on BS 8611 to this real robot, Purble, which is essentially a robot toy. It doesn't do very much, but it is nevertheless a robot. Again, this paper you can download and look at for that example of a real robot risk assessment based on 8611. Next slide, please. And here is another real robot. And this is a hospital disinfectant robot designed and manufactured by a company in Ireland. I helped them to do an ethical risk assessment, and the paper was published at ICRA conference in 2023. So there's another real robot example of 8611. And next slide, please. And the final one of my 4 case studies of 8611 is again a theoretical, it's a thought experiment paper. It was published in the Philosophical Transactions Royal Society in 2025, so earlier this year. And what we do here is that we conduct an ethical risk assessment of 4 different swarm robotic systems. And you can see a small image showing, for instance, a swarm of robots, delivery robots, a swarm of firefighting robots, aerial robots, a swarm of pollution detecting river basically robots, and a swarm of nanoparticles, smart nanoparticles, detecting cancer. So, you know, variously futuristic, not too futuristic applications. And again, we applied the method of risk assessment, ethical risk assessment in BS 8611. And you can see just a fragment of one of the diagrams, flow diagrams in that paper. So that, I think, brings me to the end of this short presentation. I hope you found it interesting. Thank you.
Many thanks, Alan. So now I'd like to welcome Jeremy Haddle. Jeremy has over 2 decades of experience in robotics and systems engineering. Jeremy has developed pioneering solutions, including autonomous inspection platforms for satellite infrastructure and AI-embedded robotic manufacturing systems. His work has supported UK national innovation programs and contributed to collaborative R&D with leading universities and industrial partners. Jeremy is a chartered engineer and fellow of the Institution of Engineering Technology and serves on advisory boards including the Centre for Robotic Autonomy for Demanding and Long-Lasting Environments. He regularly helps shape national strategy for robotics and automation and encourages horizontal innovation, the sharing of good practices and knowledge across industries to foster wider adoption of robotics. He also contributes to standards development through his role on the BSI Robotics Committee, promoting best practices and interoperability in robotic systems. He is a recognized advocate for responsible automation and regularly shares insights on the future of robotics and the transformative potential of robotics through speaking engagements, and is a passionate advocate for responsible, sustainable automation in high-value sectors. Over to you, Jeremy.
Thanks, Taki. Good morning, everybody. Could we have the next slide, please? So I'm going to talk about a slightly different field of robotics, and that's in space, where we don't actually have a lot of robotics in orbit at the moment, or even on planetary missions. And why is the space industry important, and why do we feel that robotics is very important to us? Well, the slide you can see at the moment tries to highlight this. Normally, if I could see you all, I would say, who of you used Google to get to your office or your place of work today? And many people would stick their hands up. Well, if you did use Google to get to your office, then you used 12 satellites to actually navigate to your office. It's not a very nice weather day here in the UK, and we've probably all looked at the weather forecast. Again, all that data comes from satellites. And if you passed an emergency services vehicle today, that emergency services vehicle was being controlled and directed and communicating with its base through satellite comms. So satellite technology in space underpins a huge amount of what we do. And in fact, as you can see, it's about 450 billion pounds of economic activity is underpinned by the space economy. And that's everything from communications, Earth observation, exploring our universe, our navigation and timing, our Google Maps, and increasingly industrialization. If we have the next slide, please. And when I talk about industrialization, what do I mean by that? Well, it's a commercialization of the in-orbit environment. Previously, we've really used space for, yes, for communications, yes, for Earth observation, but really it's about science. And what's happening in the market at the moment, particularly in the space sector, is we're starting to see this ability to be able to launch more often, and in the future much larger payloads, as demonstrated by the Starship picture there. And that enables us to do more things in space. It enables us to look at the space environment and say, how do we use this for a commercial opportunity? Could I, for example, manufacture new semiconductor materials for quantum computing, or new pharmaceuticals in the space environment by utilizing the very unique environmental constraints that we have in space, such as the microgravity environment and a clear vacuum. And beyond that, how do we look beyond our own orbit? How do we look at the moon? Is there an opportunity to use the moon and Mars and beyond to help us here on Earth? But that raises a really important question of how do we use space sustainably? And that's very, very important, as the next slide demonstrates. Here we go. So that picture on your left, it doesn't look like much. In fact, the best way I can describe it is if you imagine a stone chip on your windscreen, that's exactly what you're looking at. The problem is that windscreen is on the ISS, the International Space Station, which is about 400 kilometers above our heads. That's roughly about the same size. It's not very big, but that's a chip that was put into one of the viewing windows by a micrometer fleck of glass, sorry, of paint, traveling at over 17,000 miles an hour. Now, obviously, that's quite a serious impact. It's quite a heavy speed. And if you're in the ISS and this kind of object hits you, you notice it quite quickly. And we have this problem in space where we have a considerable amount of debris. Of everything we've ever launched into space, 90+% of it is still in orbit and it's floating around as debris. And the best way I can explain it is if you imagine plastics in the ocean, we've got debris in space. It's a similar kind of problem. And that debris travels very fast and can cause huge amounts of damage to all of the space infrastructure we have. Now, the image on the right is ESA's Sentinel-1 satellite. Now, a few years ago, there was an earthquake in Morocco, and ESA were going to use the Sentinel-1 satellite to understand how the Earth mass had changed around the earthquake so that they could direct emergency services and support to areas that it needed. Unfortunately, as Sentinel-1 was about to fly over Morocco, they detected a piece of debris in its way. Now, in an act which I think was very brave by ESA stuck to their guns and left the satellite where it was. They weren't sure if that piece of debris was going to hit the satellite, and if it was, it could have destroyed that huge, very expensive and crucial satellite. As it turned out, it missed by a kilometer. Sounds a lot, but in the space terms, we classify that as a near miss. But Sentinel was able to then take those images and direct people to where they were needed. But if they had to move Sentinel-1, we would have lost all those images, and emergency aid to people who needed it would have been affected. So it's really important that we start about how we sustainably use space. If we have the next slide, please. What we're starting to think about in the space industry is this concept called in-orbit service assembly and manufacturing. It's three main components. It's mostly about removing debris that we don't need, removing those thousands of objects that we've left behind, everything from huge spacecraft down to cameras, watches, and even bags of waste that have been jettisoned from the spacecraft. How do we go about removing all of that debris and cleaning up our space environment? And then for those spacecraft that are still there, how do we service them? How do we upgrade them? How do we repair them? How do we prolong their life so they don't become future debris? And then we start to think about how do we manufacture and assemble future spacecraft? How do we build these big commercial space stations that are being discussed, or even larger structures, and some of these larger structures are kilometers in size to enable space-based solar power systems, to enable future sensing systems and orbital data centers. So how do we use that assembly and manufacturing techniques from Earth to sustainably make our space environment, to sustainably improve our space environment? And if we can have the next slide, please. Now, I put this in because this is an example of a couple of robots actually in space doing these kind of tasks. And I put this in because to operate in the space environment is incredibly difficult for humans. It's the only kind of environment that astronauts will tell you tries to kill you in multiple different ways every second of the time you're there. So really, we do need lots and lots of robots up there. Our challenge is also a very difficult place to work for robots. And a further challenge is we actually don't really have a lot of internationally agreed standards. So if you can have the next slide, please. Now, I've said we don't have a lot of internationally agreed standards. We actually have a huge number of standards for operating in space, but they're all from the major space agencies. So we don't have an ISO or an IEC equivalent in the space environment. We have NASA, we have ESA, we have the Japanese Space Agency, the Russian Space Agency, all have their own individual standards. If you want to go and interact with one of those spacecraft, you need to comply to their standards, but there is no overriding governance that says this is the standard you will use. And one of the reasons for that is space is not governed by any international laws. We have UN treaties, and these treaties were written back in the 60s when the space race was around, and are not necessarily fit for purpose because they look at space in 5 key ways. They say space is a global commons. I think that's probably something we all want to maintain. We want to maintain the peaceful use of space. Well, it's debatable whether or not that's ever been agreed to. Every state has its own responsibilities. What that means is that if you are the state that launches and owns a spacecraft, even if it's a private spacecraft, the state that you've launched from is responsible for it. And that means that a Russian spacecraft is subject to different laws to an American spacecraft or a French spacecraft or a British spacecraft. We should be protecting the space environment, but to be honest, we've not really done a very good job of that, and we should be cooperating. And whilst we do cooperate on things like the International Space Station, beyond the International Space Station, cooperation in space is a little lacking. And what we end up with, if we have the next slide, when it comes through, is a bit of a Wild West scenario. So forgive me, I've used ChatGPT, but we have a bit of a Wild West scenario in space where there is no real governing body or governing set of standards that say this is the things you must do. If we have the next slide now. And so what does that mean for robots? Well, we need some harmonized international regulations. Now we have something called the EU Space Act that's currently going through the European Union. As a UK country, we're not necessarily bound by it, but if we're working with ESA, we will be bound by the EU Space Act, and it's going to put some certain restrictions on what we can do and tell us how we can do things. But more importantly, we need to leverage existing international standards that people have already talked about this morning, that say, how do we make sure that robots are safe? How do we make sure they interact with people? How are they ethical? How do we build sustainability, and how do we validate what the robot is going to do, particularly if we're working in an AI environment? These are the things that interest us around robots and standards for the space environment, and things that we really need to work with BSI and the wider community to develop but not just for the UK, but for the international space community. So that's my last slide. Thank you very much for listening. And if you have any questions, oh, this is not my last slide. I forgot this one. This is a really important picture. It's a very famous picture. Hopefully, you can just about make out a blue dot on the kind of right-hand side of the picture. That's Earth. This is taken from Voyager, just as it was about to leave the solar system, and it was looking back at Earth, and that's the blue dot. And one of the reasons we talk about sustainability and all of the things that we need to do about removing satellites, repairing satellites, is that's the only place that we know of that humans can live at the moment. So it's probably something it's very precious, and it's something we need to look after. So that is my last slide, and I will end there. Thank you very much for listening.
Thank you very much, Jeremy. Now I'd like to welcome Sarah Fletcher. So Sarah is a Principal Research Fellow in the Centre for Robotics and Assembly at Cranfield University, where she leads the Industrial Psychological and Human Factors Research Group. She has been conducting human systems interaction research for over 25 years to enhance the design and integration of new technologies and processes, predominantly in the manufacturing industry. Her work focuses on enhancing user trust, acceptance, satisfaction, performance, and safety behaviors. She leads the social science contributions in numerous UK and EU research projects and is an active participant in national and international standards committees in robotics, robot ethics, and human system ergonomics. Over to you, Sarah.
Thank you, Takia, and good morning to everybody. Just we're still in morning. Next slide, please. So I know a lot of you tuning in will probably know a lot about the manufacturing industry and how it works, but I'm going to go back to the beginning because I think it sets the scene for why I do what I do and why standards are important to what I'm trying to do. So the traditional manufacturing setup, if you go back to the first industrial revolution, we know that was to centralize production, make people work together rather than in the previous cottage industries. We divided up tasks and made assembly lines to reduce time, to reduce human motion, the skills that were needed, and the training that was needed, make everything more efficient. Management practices were employed to standardize people's behavior, so they didn't take too long breaks, so their behavior wasn't variable anymore. It was nice and consistent. And automate wherever possible to reduce that variability. And in this process, I mean, of course, you know, the first industrial revolution is made us all, and is what we all our foundations are based on. But the human factors wasn't considered really at all. And the priority is the product and the process needed to produce it. Now that remains today, and that's why I'm telling you this backstory. It meant that physical safety and ergonomics were only considered, no psychological effects. It wasn't really seen as important. The important thing was to produce something and produce it quickly. And that's led to a continuous focus on technology and automation in design. So as somebody who works in human factors and trying to think about the people, that's what I'm up against. Next slide, please. So, as a lot of you will already know, the traditional industrial robots, Jane explained this nicely earlier on. Traditionally, industrial robots were caged off. They were behind barriers. They were put away from people because the payload and speed was too high. But they were repetitive and reliable and ideal for low-skill tasks upstream in a process. And as Jane said, it's still the mainstay of production. Really, are these larger, high payload robots. That's what's needed. The disadvantage of splitting the robots away means that you have limited reconfigurability, and Jane mentioned that, and you have this segregation in the workflow because you have to put certain tasks with the robot upstream, and then further down the stream where the people are, you have to keep the robots away because they're too dangerous. That's how it's always been. Next slide, please. But what's been happening over the last 15 years or so is advances in sensing and power and force limitation technologies, and that's changed things greatly. We've had rapid development and deployment of small collaborative robots, which some people call cobots, but my boss does not like that. And, they're produced for light tasks and assistance to humans in production. So you'll see a lot of that now in mass production and in small component assembly. The robot can take on the repetitive tasks, these light tasks, and that allows the operator to focus on the more skilled work. And as Jane also pointed out, that's because we still need people. People are the mainstay of production. Robots still can't do what these can do. They still can't manipulate the way fingers can, and when there's decision making, intense decision making, complex tasks, we still need people. But the other outcome of advances in sensing and power and force limitation technologies is that we can now apply auxiliary monitoring and protective measures to the larger robots, the traditional ones that I just showed in the last slide. We can make any robot potentially into a collaborative system with protective measures, which are set out in TS 15066, like light guards and laser scanner monitoring, that sort of thing. That means the robot can still perform what we call the dull, dirty, and dangerous jobs, the things that we don't really want people to do, the things that hurt them or not good for them or they don't enjoy. But we can improve the workflow and task allocation for the operator, allowing them to do the things that are more enjoyable, more skill reliant. Next slide, please. So we now have this situation where we have a lot more human robot collaboration in industry. It improves system performance and efficiency. So of course it's going to be something that's driving the manufacturing industry. But technological advances are bringing these greater degrees of collaboration. So whereas we've spent a long time trying to put people closer and closer together with robots, but they weren't actually working interactively with them as such, it was more co-location. We're increasingly being able to put people together with a robot, so that of varying sizes and payloads, so that they can actually work alongside, not just alongside, sorry, they can work with the robot on a shared task simultaneously. And in that that theoretical diagram on the right there, you'll see sort of this, the concept that I'm thinking about, which is where you had an independent degree of collaboration moving along the scale up to full degree of collaboration. And what I'm arguing is the greater collaboration, that the more you get people closely collaborating, it means that there are human psychosocial impacts. And whereas we had the previous traditional technology focus, where people where systems were designed without consideration of people's psychological issues, it was only their physical risk. We now need to think about those. And I'm not talking about sort of clinical mental health, those issues. I'm talking about actually being able to perform with a robot, and the impact that has on your the issues like your trust in it, your confidence, your sense of safety, your sense of comfort. Those things, while they may seem soft and fuzzy, they are actually important to performance as well, and output. Because if you've got people that aren't enjoying working with a robot, or feel frightened by it, or not able to keep up with it, or even, you know, it's not working fast enough for you, it is something that can affect the efficiency and performance that was the very reason that we brought the robot in to do. So we need to make sure that we get that balance right. Next slide, please, Takia. Thank you. So are there standards that cover this? Well, no, not really. I work on robotics standards in ISO and on the BSI, and they're still very much technology focused. They look at performance and physical or functional safety primarily, or solely, and that's understandable, because when robots were in that traditional setting, when they were separated, there was a need to focus on the, you know, on them being caged off, and the people were separate. But now we're bringing them together. There's a need for something more. So the ergonomics community in standards, in ergonomics, they're starting to produce standards for robotics. One example is TR 92241-810 there, which is ergonomics of human systems interaction, and it discusses in quite a general sense the sort of things you need to think about when you're designing for people with who are interacting with autonomous systems, robotic systems. There's also one underway, and that's called the ergonomics of intelligent systems. But again, these are quite generic do's and don'ts and guidance for what to do and what not to do. There's also the ethical standards community, and Alan presented really nice overview of that. That's how you can apply that more practically to give an ethical risk assessment. But at the current time, we do not have standards that cover guidance to address the human psychosocial aspects of industrial human-robot collaboration. So while the ethical risk assessment will include a psychosocial risk assessment to some degree, it doesn't provide design guidance in the same way that other standards would. So, for example, in a robotic standard, TS 15066, you'll have a table that gives you limits of force and pressure limits. We would argue that we could develop those for human impact. So we could develop limits and guidance that advises on the limits of speed, for example, robot speed, so that it doesn't affect, so that it reaches optimal levels of human trust or human safety, that sort of thing. Next slide, please. So I've resisted the temptation to talk about my work particularly, although I have referred to it a few times, but there's a smattering of photographs here or pictures here that show all the kinds of things that we do to uncover the impacts of human-robot collaboration, and to justify that we are developing new knowledge in this area. We are understanding more about what trust in a robot or robot system is, what it consists of, what the dimensions are, how we measure it, that sort of thing. We're understanding more about the impacts of robot speed and robot proximity. We're understanding how to design personalized interactions so that robots will recognize and understand who it's working with and adapt accordingly. Things like communication interface design and understanding non-technical skills, as well as technical skills and safety behaviours, all that kind of thing, that we're able to now discover those impacts and measure and identify the limits and the ranges that we need to achieve so that we can standardise them. Next slide, please. And my last slide, just to say that the new knowledge continues to be developed. So it isn't this black art. You know, we can identify psychosocial or psychological impacts. They're not, I know they seem hidden, and it's always difficult for engineering world to sort of come to terms with that, but we can identify them and measure them and produce those metrics. We are currently proposing a new standard for ergonomics in the context of human-robot collaboration. I should have put industrial human-robot collaboration there, because that's the specific context that needs a specific standard. And I would urge people who are tuning into this to get involved. And I think Takia might mention at the end that this getting involved in standards is something that everyone can do. Thank you very much.
Thank you so much, Sarah. So now I'd like to welcome Michael Fisher as our final presenter for today. Michael is Professor of Computer Science at the University of Manchester and holds a Royal Academy of Engineering Chair in Emerging Technologies. He is academic lead for the Centre for Robotic Autonomy in Demanding and Long-Lasting Environments, co-chairs the IEEE Technical Committee on the Verification of Autonomous Systems, and is Senior Associate Editor of the Annals of Mathematics and Artificial Intelligence journal. He is partially seconded to the UK's Department for Science, Innovation and Technology, advising on aspects of AI and robotics. Over to you, Michael.
Okay, thank you very much, Takia. Thanks for the introduction, and thanks to all my colleagues for excellent presentations. I'm going to try and step back a little bit from particular robotic applications and say a little bit about, obviously, verification, because that's in the title, but why we need things like verification and why standards are going to help us in those aspects. So next slide, please. I'm going to start with why we are interested in what sort of systems we want to build. And hopefully we all want to build trustworthy systems. We want to build systems we can trust, as Sarah mentioned in the last presentation, but I'm not going to go into trust or any psychological issues. I'm going to think more about trustworthiness of these systems. So we can build systems to be more trustworthy. Whether you or I trust them is a subjective issue. But trustworthiness is really important in how we build these systems. If you think about normal systems, non-robotic systems, if you like, so the picture of the toaster on the right there, trustworthiness here is really related to reliability. You trust this toaster if it reliably burns the bread to the right color that you like. So it's essentially reliability. An awful lot of systems are like that. But when we move to robotic systems, and particularly autonomous robotic systems, it becomes more than just reliability. So picture of a famous Terminator on the right there. We know it is very reliable, but we wouldn't trust it. And it's not because of reliability. It's because we don't know what it's intending to do. We don't know why it's doing it, and we don't trust what it's hoping to achieve. So if we're going to build trustworthy systems that people actually want to use and people actually want to deploy in some places, excuse me, we need to make sure that they're trustworthy in some sense. And there's several things we need for that. One is, I think it's mentioned several times before, transparency about what these systems are doing, what's actually going on in these systems, what's inside the head of the Terminator there, and what reasons does it have for making the decisions it has. And then also verification and validation to actually check those reasons and that reasoning to make sure it is doing the right thing, and it will always do the right thing. So those things are going to be very important for trustworthiness, and as I'm going to try and argue in the next few slides, having some standards for these aspects are really important too. So next slide, please. I'm going to say a little bit about, in a very general sense, about verification and validation, mainly about verification, but let me just give you a broad sense of what's going on here. So for any systems development, you have some idea, somebody has some idea of what they want a system to do. There's a process of requirements capture that produces some specification, a more formalized specification. It might be just natural language specification, or it could be something more formal than that. So this becomes a specification of what you want the system to do once it's built. And then you go through an implementation process to build the system. And then we have a couple of arrows there, we have a couple of choices. We can check that the system is actually doing what the originator wanted. So this is essentially validation, checking the system is really what the person wanted, the people wanted when they first decided on this, but also there's verification, which is checking that the system actually matches our specification, the one we had beforehand. So these are the mottos in green there are very common views of this. So verification is, are we building the system right? Does the system match its specification? And validation is, are we building the right system? Does that system that we've built actually match what we intended in the first place? All these arrows are very important, and they're all very general. There's lots of different techniques you can use for any of these different things. There's lots of ways to do requirements capture. There's obviously lots of ways to do implementation, lots of ways to do validation, and I'm going to show you a few ways to do verification of systems. But the point being that all of these things are going to help us to not just trust these systems, but if you're a regulator, to approve these systems for use, and also as part of engineering, if you're actually building these systems, having some idea of some way of checking whether it is actually doing what you expect, and validating or ideally verifying it's achieving what you want is really important as well. So all of these arrows, we want both standards for, or at least guidance for, the whole process, how you fit everything together, but also each of the different options and how they could work. And I'm going to give you an idea of how it works for verification. So taking a system and matching it against some specification of what the system should do. And in our case, it's going to be a robotic system. So yeah, next slide. It moved on already. So excellent. So for example, there are very, very many verification techniques. A lot of these relate to software, but actually software is a very big part of most modern robotic systems anyway, especially autonomous systems. There's an awful lot of software in there that makes most of the key decisions. So there are lots of different verification techniques. I've just classified them into two parts here. So formal verification techniques, so essentially mathematical techniques to try and model what the system is doing and then try and do some analysis to see whether it's working well or not. So formal proof, things called model checking, where you analyze all the possible runs of the system. Runtime monitoring, runtime verification, some probabilistic aspects as well. And then there's empirical verification. Can you run the system in various different situations and check whether it's achieving what you want? And most of you will come across software testing, but often if you're building robots, you build simulations of these robots as well. So you test the simulation in various different scenarios, often scenarios that you couldn't actually achieve in real life. So there's lots of those things. And again, there's observational studies, there's real experiments that you can do in real life. So there's a whole bunch of different verification techniques you can use. It's important not only to have standards and guidelines for these things, but have standards that say what the benefits and drawbacks of each of these things are. They're not all equally applicable and not all equally good. You can have, let me give you just two examples. So formal proof at the top left there is a very strong technique that gives you much more certainty than most other techniques, but it's actually very hard to apply and often has to do a lot of abstraction and cutting corners. So it's quite difficult to apply in many situations. So maybe it can only be applied for one or two components in a system, but it does give you very strong confidence. If we go to the other side, something like software testing is essentially very easy to apply, but often gives you quite weak confidence. You don't really know whether you've tested all the right types of components unless you're in a very restricted environment. You can't really tell whether you've tested all the issues that might actually occur in the real deployment. So there are lots of different possibilities for verification. It's important to have both standards and guidance for each of those techniques, but also standards and guidance to work out which of the techniques you should use in which particular situation. So standards are important here. And next slide, please. Yeah, I think I've possibly said this already. They're important for the development that engineers do as they're building these systems to, you know, if you're used to building systems, you do unit tests or all those types of things quite often. They're important for obviously producing guidance for the different verification and validation techniques you might use and why you might use one technique rather than another. They're important for regulators to have some tools, techniques that they can use that they feel confident in, because there's some standards behind these tools. There's some guidance about what the benefits and drawbacks are. And these sort of things allow us to step from essentially experimentation and exploration, where we just build a robot, to actually we build a robot that's trustworthy and reliable and people actually want to use it and regulators actually want to approve the use of this thing. So these things are all very important. Next slide, please. So there are lots of standards that we need. Some are being developed at the moment, but we need more and more and more. And obviously we're talking about BSI here, but there's lots of standards organizations as well. It's important we have standards for all these things, and there's many to go at. So how do you build these systems? What's the best practice for building these types of systems? As I mentioned, verification and validation processes. How do we choose between all the different options, all the different arrows that we had in that diagram earlier on? What's the best one to choose in which particular situation? Transparency, I mentioned earlier on, transparency and explainability and understandability. How can we build the system to make sure we can understand what's going on? Can we ask the system exactly what's going on? Will it explain it truthfully? As Alan mentioned earlier on, ethical development and use is really important. Ethical risk assessment, as he mentioned, is really a useful technique. We need to have standards for all those. Security and privacy is very obvious as well. Most of these systems have lots of communication, lots of software, so they're ripe for lots of security issues. So making sure there are some standards and guidance for best practice in how to actually make these systems as secure as possible are really important, or else the trustworthiness that we talked about earlier on will go out of the window very quickly if somebody can hack into your favorite robot and take control of it. That will, yes, there won't be much trust there. Maintenance and monitoring, actually, once you built a system, maybe you've analyzed it, deployed it, that's not the end of it. You need to have, there needs to be guidance, there needs to be a whole set of monitors, a whole set of checks that you do on the system as we go along. I think as Sarah mentioned, that just building a system at the start, it changes as time goes on. So you have to be able to modify your checks, understand how it's working, understand how it's degrading, understand how it's possibly learning as well, and be able to check these systems. And then inevitably something will break. A robot arm will break or something like that, or a motor will break or a sensor will break. What happens then? And how do we build in sort of fail safes and understanding resilience in these systems? All of these things require hopefully standards that people can agree on, but at least some guidance about what the best practice is and what the options are about the different opportunities. So these are all really important things. The last thing I want to mention is that there are lots of these standards here that are being developed. We need more standards for more different things. And the last one I'm going to mention is something where a few of us are working on gradually, and hopefully this will turn into a guide or a standard one day, which is, next slide, please, which are things like sustainability in robotics. It's easy to build these robots. It's not easy to build these robots. It's possible to build these robots. It's increasingly important to build them in a sustainable way and to have some way of minimizing the environmental impact of the whole pipeline, from production all the way through to the point where you decide your robot is no longer useful and you have to either dismantle it, repurpose it, clean up the area, all those different types of things. So there's lots of different standards, various forms. There's lots more to do, but they're all useful in some form or other. So I will finish there and pass back to Takia. Thank you very much.
Thank you so much, Michael, and thank you to all the presenters today. So I'd like to welcome all panelists to the screen, just so that we can get into the Q&A session with the experts today. As before, obviously, feel free to submit any questions through the questions box. So as a start, the first question was kind of a two-pronged question, 2 points. So the first question, how do you get a common language between sectors? And the second part of the same question is how are standards impacted by legislation change? So they're quite different, but who wants to take that question? Michael?
Yeah, let me just, I think getting a common language between sectors is really important. The first thing to recognize is that there's nothing special about each of the sectors, that almost all the problems occur across lots of different sectors. And while people like to think that their particular sector scenario is special, and maybe Jeremy will say it's special, which it is, it's a very special space, but there are a lot of common problems that occur elsewhere in, for example, nuclear, if there's radiation, or in areas where you can't have communication so easily, deep sea or something like that. So there are a lot of issues that are common across, and I think understanding that there there are common problems that occur across lots of robotic systems is vitally important to understanding how to fit everything together. So that's quite a vague answer, but nevertheless.
Any,
Can I just say,
Jeremy? Oh, sorry.
I was going to say that from my perspective, yes, that there are common problems and there'll be common human reactions, but there'll also be some very specific ones too. So when I talk about industrial robots, the bigger high payload ones, there are specific characteristics of those that will bring human reactions that are different from, say, a smaller piece of technology. So yeah, common problems and common human reactions, but also some nuanced things that we have to pay attention to.
Okay. Jeremy?
I'm going to agree with Michael and Sarah, to be honest. There is a lot of commonality. Space has, as Mike said, space creates some unique challenges for us. I think a lot of it does boil down to people trusting the robots to do what they say they're going to do. And once you can overcome that, then I think we're in a good place. And we trust robots to go to Mars because simply at the moment we just can't go to Mars. We don't have the technology to be able to get us there and get us back safely. So we trust the robot to go and do the job. We need to get to a stage where we can trust robots, not just in my sector, but across all sectors, more than we do now. And it's a very difficult challenge to overcome. Partly because, as roboticists, we like to refer back to Terminator over again and over again as being the bad robot.
Thank you. And Alan?
Yes, thank you, Takia. I just wanted to make the point that standards, pretty much all standards, are completely voluntary. So even though standards are, written in a kind of quasi-legal form, there's nothing to require you to use a particular standard unless there is regulation, unless the regulator says you must use this particular standard, otherwise your whatever it is vehicle will not be approved for use. So I think it's important to understand that difference between standards and regulation.
Great, thank you. Okay, so the next question is, are there any new study groups formed for reviewing existing standards or creating guidelines for robotics and AI standards? I could answer it, but I'm going to put it over to you all to answer. Anyone want to take it? Okay, I'll just say that obviously, as the National Robotics Committee, we are obviously positioned and posed to review existing standards and create new standards in terms of robotics. We would also have a committee that's available and working on AI standards. And then within that, we would talk to one another. So there'd be people like myself who are standards development managers. We're speaking to our colleagues, and then people like our experts who are speaking today, who are talking to industry partners, and they're obviously working within their organizations to make sure that we can try and keep up with whatever's happening in industry, and that this can be reflected as best as possible in standards, which, as Alan plainly put before, they are in the majority voluntary to take on, but we do try to make sure that we've got a diverse group of people sitting and working together to make sure that when things are changing, or if a standard becomes defunct, we say, okay, this standard needs to be reviewed or this standard needs to be withdrawn. So as a quick point, I don't know if anybody else wants to add anything else on top of that. No, seeing no hands. Okay, so the next question is, so I would like to know, what about functional safety with robotically assisted surgical robots? How to integrate the regulation machine to this field, and what is the line mark? Any suggestions or points for reflection? Michael?
Yeah, I'm not an expert in this area, but I'll have a go. So my understanding is the robotic surgery thing is essentially remote controlled robotics, that there's a surgeon haptically controls something from a distance, essentially, and the robotic, I don't know what end effector does it, the actual surgery. In which case it's almost all about reliability. It's almost all about testing and understanding the reliability of these particular things and making sure that the movements that the surgeon makes are actually reflected in the movements that the robot makes. And I'm not saying that's not difficult at all, but it falls a little bit more under sort of standard engineering. You know, how reliable is this thing matching what you actually want it to do? You know, when I pull this lever, does it actually move in this way? So I assume there's lots of testing involved in this to make sure that they work under lots of different scenarios. Yeah. And because you have some idea of what you want to do, some, you know, fail safes and monitors to check that it's not going too fast or any of those types of things.
Okay, great, thank you. Alan?
Just to make the small point that I'm pretty sure there is not a standard for you know, the Da Vinci type robot, which is the you know, the kind of robot that Michael was referring to, remotely controlled surgical robot. But there are more general safety standards in healthcare robotics.
Perfect, thank you. So the next question, what standard best practices can you recommend for other countries wanting to integrate robotics in their work sectors? What is the end goal of robotics when it comes to people who had been doing the work taken over by robots? Do you foresee people stopping to work completely or finding new and meaningful things to do? Jane?
It's a difficult one around the other countries. I mean, the ISO standards go across all countries and are translated into many different languages. So they're a really, really good start. So, you know, if you're looking for best practice, then you would probably lean into that. And there are a number of sort of, you know, go-to sort of like UK, US, European standards, European and US standards are probably the primary ones that other countries would go to start with. From the point of view of, sorry, just repeat the end of the question again. I've just lost my train of thought there. The person, like that, maybe being replaced by the robot. What we are seeing in industry is that the actual use of robots is generating a whole new range of activities. So you might be taking a human out of a really dull, boring task, or a repetitive task, or something that is causing, the ergonomic issues that Sarah mentioned. They're aimed at taking over those tasks and taking people out of dangerous situations or repetitive situations. That then gives those individuals the opportunity to sort of like innovate on what becomes, sort of like the next task to look at. And we are seeing people move into sort of like those more innovative sort of like design activities, and new jobs are being created that haven't been thought of before. So you might not know the name of that job now, but actually a few years down the line, there will be a whole new range of activities that someone then moves into. So like any innovation, there's fear of what might happen, but actually we're already seeing all the jobs being created. So I don't think it's something that needs to be afraid, sort of frightening for people to be afraid of. I think it's something to be embraced and look at what it can do for you, because there'll be new things that we can do that we've not even thought of yet, that robots will help us do, or a technology that comes from the robot will then manifest into.
Thank you. Michael?
Yeah, I was going to say two things, one of which Jane's just stolen and said exactly what I was going to say. Yeah, that is that a lot of the robotics systems we're developing are to move people out of unpleasant environments. And we talked about nuclear, Jeremy's talked about space, inspecting sewers, various different really unpleasant things, working with chemical waste, all that sort of stuff. So putting robots in those places, hopefully they'll benefit the people in that they won't get quite as ill. I think the other thing, since we mentioned robot surgery in the last question, steps forward such as that, I don't think are going to put surgeons out of a job. I think they're just going to retrain to use these things, but it hopefully makes the whole system more efficient, and we can actually get the health service backlog moving in some sense. So there are benefits elsewhere as well.
Great, thank you. Next question is, how do UK regulations align with US and EU regulations for robotics? Jane?
I think we sort of touched on this in the previous question around sort of standards and international standards. I think there are individual country standards, obviously, because there's different cultures and different sort of requirements of home legislation. But I think there is a benchmark that runs across a lot of those countries around sort of reaching into ISO standards. So you will get differences and nuances just because of cultural requirements, physical constraints of sort of different types of population and different sort of environments that they need to work in. However, I think the alignment of sort of the ISO standards you do see in legislation. I've dealt with industries in a number of our sort of like different sectors in different countries, and the commonality is actually sort of quite reassuring. Really, you're not finding differing standards. Everything sort of runs to sort of like more or less the same sort of goals in slightly different ways, but and those are ISO standards sort of give you that governance across those sectors, because it's like the 45,001, the 9001 for quality, that type of thing. They do run in sort of the majority of countries.
Thank you. And Alan?
Yes, the thing about regulation is that typically each country has its own regulator. So for instance, for industrial robot accidents, if there are any, well, there are, they do happen. In the UK, it's the Health and Safety Executive that is the regulator that would be responsible for setting up an accident investigation, for instance. And other countries would have equivalent regulators that would have that responsibility. So typically regulation is all I'm saying is regulation tends to be country to country, but standards will apply, as Jane said, across different countries.
Great, thank you so much. And our final question is, as robots become increasingly prevalent and integrated into various manufacturing processes, technical and engineering support personnel may develop a sense of over-familiarity, potentially leading to a diminished perception of associated risks. What strategies can be implemented to enhance health and safety from cultural and psychological perspectives? Sarah?
I think I touched on this, and I before I start speaking, I don't have the answer, but I can say that we are working to understand those things. They will vary. The impacts of people having to work more closely with robots, as we've just discussed, are beneficial potentially, but that depends on us doing it in the right way and bringing people along with us so that they trust the robots, as Michael said. We need to design them so that they are trustworthy, that people have a sense of safety, that they do trust that they're going to do what they were going, they're intended to do. And I think that will happen. I think we as a community in robotics, I think we are working towards that, and the standards are that I listed are showing that that's the case. We are finding out what these things are that we need to pay attention to. So I don't have an answer. I can't say, well, this is what you need to do, because it will depend on the context to a large extent anyway. I can't say this is the prescription, but you know, please do have faith that I think we are as a community moving towards answering those questions. Don't know if that was helpful.
Great. Thank you. Alan, did you want to come in? Yeah.
I do, yes. In fact, I have a two-word answer to the question, and the two words are ethical governance. So standards typically need to be employed within a bigger framework of ethical governance. And in fact, I published a paper back in 2018. It's now my most cited paper, and the title is the ethical governance of robotics and AI systems. So so there are frameworks, and I think that's you know, that those frameworks provide that overall kind of oversight that you need, within which standards and regulation, of course, are critical.
Thank you. Jane?
Yeah, this is a problem that we've already encountered when we've been setting up our sort of factory of the future demonstrator. We found a sort of like trying to give people sort of a sense of sort of awareness that a robot is going to be in use has been one of the challenges, and it's something that we brought the HSE sort of portfolio holder for robotics in on, because the standards that are provided at the moment really sort of refer to andon systems and stuff. So green, a robot, you think, well, green is great on an andon system, but that actually means the robot's working. Rather than it's not safe to approach because it's working. But you know, you want to try and foster an environment where the operator of the robot or the collaborator that's going to go and work in that cell knows when it's safe for them to do so. So we've experimented with some sort of like visual lights on the floor, and the sort of like haptics and sort of like different light sensors. And I think this is where standards become really important, because we've got a number of existing standards, and we need to make sure that sort of like for manufacturers and sort of operators to keep pace with adopting those, that you can pick the right element out of other standards to then sort of like contribute to your workspace. And the colours were certainly one of the challenges that we have. So like, what colour do we then suggest to an operator that sort of, you know, sort of like indicates that that's actually working? Because the red around the edge of the floor sort of like stops people from entering, but the green is telling you that it is operational. So understanding that, and then sort of getting other systems knitted into that. So, you know, it at the moment, it has to be sort of like haptic and visual warnings, and sort of environments that sort of give you that indication. But I think as we move forward, and you know, the use of AI and those sort of things that will come in, there will be better ways of communicating with operators around sort of like situations that then sort of become hazardous, or are about to become hazardous because the robot is going to initiate movement and sort of like drawing people away. Thankfully, things like sensors and stuff keep people away from those warning zones, or from those zones at the moment anyway. But we will see this develop and mature relatively quickly. So I think, you know, again, sort of like inviting people to come in that might have knowledge about that and sort of become part of the standards committee, just then think of new ways of sort of like actually providing good practice guidance is really important.
Great, thank you. I did say that was the last question, but we do have one more. So Michael, did you have something else to add on that?
A quick comment about that, and again, I don't have the answers either, but I think the move from one person doing something to one person with a robot doing something to multiple people with multiple robots doing something, this sort of science of an understanding of how to build teams that work together, and the roles within the teams are rewarding, not just safe, but rewarding to the members of the team as well, is really important too. And how you construct those teams so that the human doesn't become just a cog doing nothing useful at all is really important. So I'll go back to you, Takeo.
Great, thank you. So this last question just pipped us. So this is a new committee member of a BSI committee, and they have noted that their committee is developing a technical specification or possibly standards in future for explosion-proof robots, including drones. I'm aware that we are now working with other ISO technical committees. As per their network in the National Robotitorium in UK, and there are also many IEEE standards for robotics. So the question is there a collaboration between IEC and IEEE for creation and maintenance of standards for robotics? For example, is explosion-proof robotics? And yeah, that's the question. Alan?
Well, having worked both as a volunteer for BSI and the IEEE, my experience is no, but there should be.
Okay, great. Anything else to add from anybody else? Because I mean, that's a very simple answer, isn't it? So thank you. That's all of the questions. So I will just note, thank you so much to everybody for attending today, and thank you so much for, to Alan, Jane, Michael, Sarah, and Jeremy for giving over their time and expertise to speak with us today. You can see on the screen here, we mentioned BS 8611 a few times. That standard is available to go and have a look at and purchase via the link. You have my name, and you obviously have the name of the other speakers here today. So please do reach out to us if you have any questions, or if you would like to know more about joining any national committee, but obviously the robotics committee is the one that we're focusing on today. And yeah, thank you for your time, and we shall hopefully see you all again soon. Thank you. Bye. Bye, everybody.